I said I would do the video, so here it is. The first one was this thing here. X approaches k from the left. First thing you do is plug in, and no matter what k is, the top is going to be positive, and when you plug in k, the bottom is going to be 0. So this is a case of non-zero over 0 with the direction specified. So the answer either has to be positive or negative infinity. So when we plug in numbers just less than k, numbers just less than k minus k are just less than 0, and so the bottom is negative while going to 0, and the top is positive. So the limit is minus infinity. Sine x over x squared, x approaches 0. We're going to want to do this just like any other one of the sine ones. You're going to want to separate one sine from one of the x's, and it'll be the limit as x approaches 0 from the right. When you sequester those, you'll get sine x over x multiplied by 1 over 10x. So as x approaches 0 from the right, this portion of it goes to 1. And this, because it's 0 denominator with non-zero on top, is going to go to positive infinity. Third one, we haven't seen anything exactly like this, but I was hoping that you would get the idea. This is supposed to be an x. As x approaches infinity, this gets really negative, which makes the exponential very, very small. So small, in fact, that it goes to 0. And the only thing that's remaining after that is the 4 divided by 2. So this limit is 4 over 2, or 2. This limit is the factor and cancel one. When you plug in 2, wait a minute, I think it was actually negative 2. Yeah, it was negative 2 from the left. But when you plug it in, you get 0 over 0. So you know that there's a factor of x plus 2 in here, so you factor it. X plus 2, x minus 3. And then this will cancel with the top. And then you can plug in the minus 2. Minus 2 minus 3 is 5. So the answer to this one was minus 1/5. The radical one had, alright, so there's one radical, and x is approaching infinity. So the first thing that we're going to want to do is figure out what the sign of the answer is going to be, because we're going to do an operation and invert it on the top. So as x approaches infinity, the top is positive and the bottom is positive. So the sign of the answer, if we do get a number, is going to be positive something. So to pull the radical over the entire thing, you're going to have to cube root this, and cube it at the same time. So that when you do that, you'll have the limit as x goes to infinity of just one expression. And when you multiply this out, the first term that you'll get will be 8x cubed plus stuff we're not really worried about, because only the highest term matters. And on the bottom, you're left with a regular x squared. So you know plus 4. So you know that the argument on the inside, that's a cube root. The argument on the inside, since the higher exponent is on top, the whole expression is going to infinity, and so the whole thing must be going to positive infinity as well. The piecewise one, I think, was find the value of c that makes f of x continuous everywhere. So you have to equate the left and right limits as x approaches negative 2. So when you plug in negative 2, you get 4 minus c, that one. And on the bottom, you'll get 4c minus 11. So all you have to do is solve for c, bring the 11 over here, you get 15, equals, bring the c over there, 5c, so therefore c is 3. This was the plug-in one. All you had to do was plug in x equals 1, and you get 4. 7 minus 4 is 3, 4/3. Here's the absolute value one. As x approaches 0, we want to get rid of the absolute value bars and then try to reevaluate the problem from there based on what the argument is. But in the vicinity of 0, the quantity x plus 2 we know is going to be positive. So while this is really the limit as x approaches 0 from the right, of x plus 2 minus 2 over x. The absolute value bars don't mean anything. So once they drop, we cancel out these 2's. Once they go, the x's go, and the limit will just be 1. Alright, the cosine one, this one is, if you just ignore the 4, it matches the special cosine limit that we did in class. It was either 1 minus cosine x, or it could have also been cosine x minus 1. Minus the quantity. But either way, it's going to go to 0. The 4 on the bottom doesn't make a difference. If you tried to conjugate it, you would have had to do a little bit more work, but you would have come to the same answer in the end. This special limit is 0. The limit as x approaches minus infinity of e to the 99, which is a very large number, divided by x. But as x goes to minus infinity, this is still getting very, very, very large, and so much so that it's eventually going to blow this away, and so it's really ultimately not any different from like 1 over x or any other rational function where the degree is higher on the bottom. So this limit, degree is higher on the bottom, is going to go to 0. This was one that you just had to know. You need to know that the logarithm graph looks like this. Grows very slow, but as you approach 0, it goes down to minus infinity. For this cosine one, we did a couple of these in class. As x goes to infinity, you can just ignore the cosine and look at the argument. And since the argument has the same degree top and bottom, nothing else matters. The argument is going to go to pi over 3, which is to say that the final thing, you're going to be taking the cosine of something that's approaching pi over 3. So the answer is the cosine of pi over 3. So you draw out the triangle just to remember, 2, 1 radical 3, pi over 3 is 60 degrees. So the cosine of 60 degrees is 1/2. Okay. Now we got coming up right here. For x is greater than or equal to 0. For x is greater than or equal to 0. It says y equals 2 is an asymptote. And then it asks which of these are true. Well, if the function has y equals 2 as an asymptote, I'm just going to sketch it in here. That means, here's 2. That means that the function at some point has to do something like this and approach positive 2. Alright, that's what an asymptote is. An asymptote is end behavior. It is a limit at infinity. I specified x is greater than or equal to 0, so we're only talking about things in this direction. So which of the following must be true? F of 0 does not have to be 2. F of 2 is undefined. That doesn't have to be true. F of 2 is not even mentioned in the problem. The limit as x approaches 2 is infinity. Again, it has nothing to do with anything. It just wasn't relevant. And this is the one that it is. A limit at infinity is an asymptote. So for the line y equals 2 to be an asymptote, when x for positive x, this must necessarily be true. Here was the intermediate value theorem problem. I gave you select values of x and g of x. And I said that g of x was continuous, and we wanted to find find an interval such that g of x had to have 2 zeros in it. So what you do is you draw it out. You say here's minus 2, 0, 2, and 5. Now the value, so it's minus 2 here, minus 5 here, g of 2 is 3, and g of 3 is minus 3. So the function's got to look something like this. Alright, g of x is going to be something like that. It had to have 2 zeros. I forget what the answer choices were, but it was anything that contained 0 and 5. Anything that contained 0 and 5 would have qualified as an answer. I know that some of them were from minus infinity, say, to minus 1, right? But a function doesn't have to have any zeros there. We don't know what g of x looks like otherwise, but since you know it crosses between 0 and 2, it's got to have one 0 between 0 and 2. And since you know it crosses between 2 and 5, it has to have another 0 between 2 and 5. So the answer was actually anything that contains 0 and 5. I believe the answer was all the way on the right, and that was, I think it was something like minus 1, 5. But that's what you had to look for with that one. Oh, and the true-false. Let's see. The first one, the limit as x approaches a from the right of f of x does not equal the limit as x. Let's see. Yeah, the limit as x approaches a from the right does not equal the limit as x approaches a from the left. Therefore, the limit of f does not exist at x equals a. That was true. Right? If they go to different spots, then it's a discontinuity, and the limit does not exist. If f is continuous at x equals c, it's supposed to be a c, then the limit as x approaches c is f of c. That's false, because you could have a situation like so, where the limit exists, but the value is something else at that point. So that's false. Next one, the limit as x approaches c is L. That implies that f of c equals L. Oh no, wait, no. This says if f is continuous at c. Okay, yeah, never mind, scratch that. If f is continuous at x equals c, then it must be the case that the limit as x approaches c of f of x equals f of c. That is the definition of continuity. So that one is definitely true. Okay. Okay. This is what I was talking about with the latest problem. The limit as x approaches c is L. Does that imply that f of c is L? No, because once again you could have a situation like this, where the limit is this y value, but the value of the function is something else. So that's false. The limit as x approaches c of g of x exists, but the limit as x equals c of g of x does not equal g of c. That's exactly this situation here. If that's the case that g has a removable discontinuity at c, and that is true, the definition of a removable discontinuity was that the limit existed. So that one's true too. And the very last one, is this function continuous everywhere? And you know that this function has a hole at 0, 1. So this is redefining the function so as to fill in that hole with this value of 1. So since the limit as x approaches 0 is 1, then yes, this function is continuous everywhere. And that is the limits test for the extra credit. I'll do the extra credit right now, though. First period had this one. Alright, we let n be given, find an n such that this function will be greater than m whenever x is in excess of n. So what we had to do was, it was tough because it has two x's in it, but you have to find something to compare it to. So if you factor out an x from here, you get x minus 5 minus 10. If you want to show that something is large, find something that's less than it, which is also getting large. So if you factor it out like this, it's easy to see that what's less than this is if we replace this x with x minus 5. Then the whole thing will be less than what we have written here. So we just extend the inequality this way, and we'll write x minus 5 quantity squared minus 10. And if we can make that greater than m, then we'll be in business. So all we have to do is take this, isolate m, and then work backwards from it. So we'll start with add 10. Alright, this is x minus 5 quantity squared can be made is greater than m plus 10. And then we take the square root, x minus 5 is greater than radical m plus 10. And then x is greater than radical m plus 10 plus 5. So that's it. This is where we start now. We let this number be n. Right? And then to finish it off, we will say let m be given. And so we'll say if n equals, can you see that? If n equals radical m plus 10 plus 5, it must be the case that x plus 5 is greater than radical m plus 10. And if that's true, it must also be the case that x plus 5 squared is greater than m plus 10. And then it must also be the case that x plus 5 quantity squared minus 10 is greater than m. And if that's the case, then it automatically follows that if I can fit it in there, this x minus 5 minus 10 is greater than m. And that completes the proof, because this is equal to x squared minus 5x minus 10. So that shows that for any value of m, this function can be made greater than it by choosing n to be this particular number. Similarly, similar instructions were for the one I gave 7th period, and that was this. If you let n be given, find a value of n such that this function will be greater than m when x is greater than m. So once again, if you want to show something is big, find something smaller than it. So preferably something nice and easy to work with algebraically. So what you do is, the best solution I saw, this is the way that I did it, was I compared this to x squared minus 4 is over x minus 2. See, this is less than this because the denominator is smaller. But because of the cancellation, this equals, right, this factors in x plus 2, x minus 2. And once you cancel those factors, this is going to equal x plus 2. So if it can be shown that x plus 2 is greater than m, then it will necessarily be the case that this will be greater than m. So to show you how this works, so we want this to be greater than m, so the value of n that's going to work should be m minus 2. And let that be so. So we'll say let m be given, and let x be greater than m minus 2. If that's the case, x is greater than m minus 2, then it must be the case that x plus 2 is greater than m. And if x plus 2 is greater than m, well, if you just multiply top and bottom by x minus 2, right, so you get x minus 2 times x plus 2, that equals x squared minus 4 over x minus 2. But that is less than x squared over x minus 2, and that shows by the chain of inequalities that the function will be in excess of m, and that completes the proof.